Tonight, Hubble has caught something so strange that it almost looks impossible. A glowing trail in deep space that may point to a supermassive black hole escaping its own galaxy. Welcome to Sleepy Space. In this journey, we'll follow the evidence, the mystery, and the unanswered questions behind this cosmic runaway. Before we begin, leave a comment telling me where you're watching from. At first, it looked like the kind of thing an astronomer is trained not to trust. A thin, sharp streak of light cut across the blackness behind a distant galaxy, so narrow and straight that it almost felt too artificial to belong there, like a scratch on old film or a glitch hiding inside the image. Hubble has seen galaxies colliding, stars dying, nebulae glowing like painted smoke, and deep fields crowded with ancient light. But this was different because it did not announce itself with beauty. It appeared as a line, a quiet mark in the dark, the sort of detail a tired human eye might pass over after hours of staring at data. And that is what makes the discovery so unsettling in the best scientific sense. Sometimes the universe does not reveal its strangest secrets as giant explosions or dramatic spirals, but as something so small on the screen that it can almost be dismissed before anyone realizes what they are looking at. The astronomer Peter van Dokkum was examining a Hubble image when he noticed the streak near a distant galaxy, and the first reaction was not instant certainty. It could have been a cosmic ray, one of those energetic particles that strike a detector and leave behind a false trail. It could have been an artifact from the instrument. It could have been a background object lined up by chance. In astronomy, the first rule of mystery is restraint, because the sky is full of illusions created by distance, motion, dust, and the limits of our own instruments. But the more carefully the image was checked, the harder it became to treat the line as noise. It was not just a random mark. It seemed connected to something real, stretched across space in a way that hinted at motion, violence, and an event that had unfolded long before humans ever built telescopes. The line was not floating alone, like an accidental beam. It appeared to point back toward a galaxy, as if something had been thrown out from that galaxy and had carved a path behind it. That single possibility changed the mood of the image. A flaw in the data would be forgettable. A narrow trail connected to a distant galaxy could be evidence of something far stranger. A massive, invisible object moving so fast through intergalactic gas that it may have triggered the birth of new stars in its wake. The idea sounds almost backwards at first, because when people hear black hole, they usually imagine a cosmic drain, something that swallows light, matter, and anything unlucky enough to come too close. But this Hubble image suggested a different kind of story. One where the black hole was not sitting at the center of a galaxy like a dark king on a throne. It may have been exiled. It may have been racing away. And behind it, instead of leaving empty destruction, it may have left a glowing trail of newborn stars. That is why the streak mattered. Not because it was bright, but because it was wrong, in exactly the way a real discovery often is. It did not fit neatly into the ordinary catalog of galaxy shapes, gravitational arcs, jets, or image defects. A galaxy can have tidal tails, stretched by the gravity of another galaxy during a collision, but those are usually broader, messier, and shaped by the pull of entire systems. A black hole can fire jets when matter falls into it, but those jets often come from active galactic nuclei and show a different relationship to their host. This line looked like a long wound or contrail across deep space, thin enough to make scientists pause and long enough to demand an explanation. The scale is difficult to feel because Hubble images compress the unimaginable into something that fits on a monitor. What looks like a faint streak could span roughly 200,000 light-years, about twice the width of our Milky Way's bright stellar disk. That means light itself, traveling at the fastest speed nature allows, would need 200,000 years to cross it from end to end. And yet, in the image, it is only a line. This is one of the strange tricks of astronomy. The grandest structures in the universe can appear almost fragile when distance presses them flat. But if that line is what researchers think it may be, it is not fragile at all. It is the aftermath of a gravitational event so extreme that a supermassive black hole, possibly weighing millions of times the mass of the Sun, was launched from its home galaxy like a stone from a sling. The word launched sounds too simple for what may have happened. Nothing touched it. No engine pushed it. No explosion kicked it out in the way a blast might throw debris across a room. The force would have been gravity, operating over immense distances through the chaotic dance of merging galaxies in the black holes hidden in their cores. When galaxies collide, their stars usually do not smash together directly, because the spaces between stars are enormous. But their gravitational fields overlap, distort, and rearrange everything. Gas is compressed, star formation can ignite, spiral shapes are torn apart, and at the centers of those galaxies, supermassive black holes may begin moving toward each other. If a third galaxy enters the story, carrying its own central black hole, the system can become unstable. Three massive objects interacting gravitationally can trade energy in violent ways. One may be flung outward while the others recoil or bind together more tightly. It is a cosmic version of a slingshot, but played out with objects so massive that their motion reshapes the fate of entire galaxies. The Hubble streak may be the clue left behind by one such ejection. And that is where the discovery becomes more than an unusual photograph. It becomes a forensic scene. The distant galaxy becomes the possible place of origin. The thin, glowing line becomes the trail. The bright knot at one end becomes a possible sign of shock-heated gas or fresh star formation. And the invisible suspect is a runaway supermassive black hole, moving through space with enough speed and mass to disturb the gas around it as it goes. Hubble did not capture the black hole itself, because a black hole by definition does not let light escape from within its event horizon. What Hubble saw was consequence. That is often how the universe forces us to study its darkest objects. We do not see the thing directly. We see what it does to everything around it. We see stars orbiting something unseen. We see gas heating as it falls inward. We see jets, radiation, gravitational waves, warped light, or in this case, perhaps a trail of stars born in the wake of a silent traveler. There is something almost poetic in that, but the science is sharper than poetry. If a black hole is moving through a region of thin gas at high speed, it may compress that gas rather than simply consume it. Under the right conditions, compressed gas can cool and collapse into stars. So the trail could be a luminous record of movement, each young star marking a place where the passing black hole disturbed the intergalactic medium and left gravity's fingerprint behind. Still, the word could matters. A good mystery in science is not a license to pretend every answer is already known. Researchers have to ask whether the streak might be something else, an unusual galactic feature, a jet, a chance alignment, or a structure produced by interactions that do not require a runaway black hole. The reason this case became so compelling is not that one image solved everything, but that the image raised a question powerful enough to demand follow-up. That is the heart of real discovery. It does not begin with certainty. It begins when a detail survives the first attempts to explain it away. The streak survived. It remained there after the easy answers weakened, and once it remained, it turned an ordinary observation into a doorway. Through that doorway is a story about galaxies merging, black holes being thrown from their centers, and the possibility that some of the universe's darkest objects may wander through the emptiness between galaxies, almost invisible, unless they happen to leave behind evidence bright enough for a telescope like Hubble to catch. What makes this especially gripping is that Hubble was not built yesterday. It has been watching the universe since 1990, repaired, upgraded, and kept alive through decades of scientific ambition. It has looked deeper into space than any human eye could ever manage alone. And still, after all these years, it can catch something that feels new enough to make scientists stop and reconsider what they thought they knew. The image is not just a picture of a strange line. It is a reminder that the universe is not fully mapped, not even in the places where we think we are only seeing distant background galaxies. Hidden inside those backgrounds may be motion, violence, exile, and creation happening on scales the human mind can barely hold. A supermassive black hole, if that is truly what this is, should normally belong in the dense heart of a galaxy. Seeing evidence that one might be racing away from its home is like finding a lighthouse torn from a coastline and drifting across the ocean, leaving glowing islands behind it. It is not supposed to be there, and yet the universe is full of things that are not supposed to be there until the evidence becomes too strong to ignore. That first strange streak in the Hubble image was the beginning of the chase. It was the faint clue that led astronomers toward one of the most unusual possibilities ever suggested for a black hole. Not a monster waiting in the center of a galaxy, not a distant engine feeding on gas, but a fugitive moving through the dark, carrying no light of its own, known only by the trail it may have forced the universe to create behind it. The moment the strange line was treated as something real, its size became the next shock, because this was not a small streak near the edge of a galaxy or a short plume of glowing gas that could be explained away as ordinary galactic weather. It stretched for roughly 200,000 light-years, a distance so large that it becomes almost meaningless until you compare it to something familiar. The Milky Way, our entire home galaxy, is about 100,000 light-years across, meaning this single narrow trail could span nearly twice the width of the stellar city that contains our sun, our planets, and every night sky humanity has ever looked up at. In a Hubble image, that kind of distance is flattened into a thin, pale mark, almost delicate, but the reality behind it is enormous. Every point along that trail represents a place in deep space where light, gas, gravity, and motion may have interacted over millions of years, creating a structure so long that if one end were placed near our solar system, the other would vanish far beyond the reach of anything we could imagine as local. And yet the line is not just long, it is strangely narrow, almost too organized for a normal tidal tail, too extended to be a simple burst of star formation, and too connected to a directional event to feel random. That shape is what gives it power. The universe is full of messy things, galaxies warped into arcs, clouds shredded by radiation, debris pulled out during collisions, filaments of gas stretching between clusters. But this trail seems to tell a cleaner, sharper story, as if something passed through the darkness with speed and purpose, leaving a luminous record behind it. NASA described it with an image people can understand, a contrail, like the white streak a jet leaves behind in Earth's sky. But this is not vapor behind an airplane. This is a possible trail of young stars and disturbed gas across intergalactic space, drawn on a scale where human comparisons almost break down. A jet contrail fades within minutes. This cosmic trail has persisted long enough for its light to cross billions of years and reach a telescope orbiting Earth. That contrast is where the mystery deepens, because a line like this does not simply sit there as decoration. It demands a cause. Something had to disturb the gas. Something had to move through or near it. Something had to organize that disturbance into a path so long and narrow that astronomers could follow it backward, like a footprint in fresh snow. The most intriguing possibility is that the trail is made of stars, born in the wake of a runaway supermassive black hole. But even before naming the culprit, the trail itself deserves attention, because it may be the visible part of an invisible process. Stars do not appear from nothing. They form when gas becomes dense enough and cold enough for gravity to take over, pulling matter inward until nuclear fusion ignites. In galaxies, this often happens inside giant molecular clouds, regions already rich with material. But between galaxies, space is far thinner, more empty, and less friendly to starbirth. So if a long chain of young stars really exists out there, the question becomes sharper. What compressed the gas enough to make it shine? One possibility is motion. A massive object racing through thin gas can create pressure, shocks, and turbulence. It can push material aside, squeeze it into denser regions, and leave behind conditions where stars may begin to form. The trail then becomes not just evidence of something moving, but evidence of something moving with extraordinary influence. A normal star could not carve a wake like that across 200,000 light-years. A small black hole could not easily account for that scale. A supermassive black hole, however, carries gravity like a hidden engine. Even if it emits no light of its own, its passage could disturb the environment around it in ways that remain visible long after it has moved on. That is the strange beauty of this discovery. The brightest part of the story may not be the object itself, but what the object forces the universe to reveal. Along the trail, the light appears bluer than one might expect from an old population of stars, and that matters because blue light often points toward young, massive stars. These stars burn hot and live fast, so when astronomers see them, they are usually looking at relatively recent star formation, at least on cosmic timescales. Old stars tend to glow redder and quieter. Young, massive stars shine with a fierce blue-white intensity before dying quickly. So a blue trail is not just a pretty color in a processed image. It is a clue about age, temperature, and origin. It suggests that the trail may not be a leftover stream of ancient stars pulled out of a galaxy long ago, but a place where stars may have formed after the event began. That distinction changes everything. If the trail were merely old stars stripped from a galaxy, the story would be one of destruction and removal. If the trail contains newly formed stars, the story becomes stranger. A dark object may have triggered creation as it fled. This does not make the black hole gentle or alive or purposeful. Science does not need those kinds of fantasies to be dramatic. It simply means that under extreme conditions, the same gravitational chaos that tears systems apart can also create new structures. The universe is rarely only destructive or only creative. It is usually both at once, depending on where you stand and what timescale you are willing to imagine. The trail's length also acts like a clock. If a black hole or another massive object made it while moving away from a galaxy, then the distance of the trail and the estimated speed of the object can help reconstruct how long the journey has lasted. Researchers have suggested a timescale of tens of millions of years, which sounds ancient from a human perspective, but is recent in the life of a galaxy. 40 million years ago, Earth was already alive with mammals, forests, oceans, and weather, but no human mind existed to look up and wonder about deep space. While life on our planet evolved quietly, something far away may have been tearing through intergalactic space, drawing a luminous scar behind it. By the time Hubble detected the light, the event was already history, preserved not in stone or ice, but in photons crossing the universe. That is another layer of the mystery. We are not watching this structure in the present moment as it exists now, over there. We are receiving an ancient message delayed by distance. Astronomy is always archaeology with light. The farther we look, the older the evidence becomes. So this 200,000 light-year line is not only a structure in space. It is a preserved chapter from the past, arriving late, still carrying enough detail for scientists to reconstruct a violent gravitational story. And the more one thinks about the scale, the more unsettling it becomes. A trail longer than the Milky Way is not something produced casually. It implies a sustained process, not a single flash. Supernova explosions can be brilliant, but they expand outward and fade. Active galactic jets can stretch enormous distances, but their shape, radiation, and connection to a central engine usually carry recognizable signatures. Tidal streams can curve elegantly around galaxies, but they tend to show the broad fingerprints of gravitational pulling. This feature, by contrast, appears like a narrow path through space, which is why the runaway black hole idea gained attention. It fits the visual logic in a way that feels almost cinematic. An unseen mass ejected from a galaxy, racing through thin gas, leaving behind compressed regions where stars ignite. But fitting a picture is not the same as proving a case. Scientists must be careful because space can fool the eye. A distant background galaxy might align by chance. A jet might appear unusual because of viewing angle. Gas shocked by some other interaction might mimic a trail. The honest version of the story keeps those doors open, not to weaken the mystery, but to make it real. The most exciting scientific claims are the ones that survive alternatives. That is why the trail matters so much. It is a test. If it is truly a wake of star formation behind a runaway supermassive black hole, it may become one of the clearest examples of a black hole expelled from its galaxy and caught indirectly through its effects. If it turns out to be something else, it will still teach astronomers about rare structures and strange alignments in the distant universe. Either way, the line is valuable because it refuses to be ordinary. It sits there across the image, thin but enormous, quiet but impossible to ignore, asking how something so dark could leave behind something so bright. And that question is what pulls the viewer forward, because once the trail is understood as a clue rather than a picture, the story changes from Hubble saw a streak into something far larger, a chase across deep time, where the only way to find the invisible fugitive is to study the stars it may have awakened behind it. At the forward end of the luminous trail, the mystery becomes stranger, because the suspected object is not something Hubble can simply point at and photograph like a planet, a star, or a glowing cloud. The leading candidate is a supermassive black hole, possibly around 20 million times the mass of the Sun. But if that is truly what sits at the head of this structure, it would not appear as a bright object with edges and color. It would be almost the opposite, a place where light itself cannot escape once it crosses the boundary known as the event horizon. That is why the discovery feels so unusual. The trail is visible, the surrounding clues are visible, the possible shock-heated gas is visible, the young blue stars may be visible, but the thing powerful enough to organize the whole scene could be dark. It is like seeing a long wake across a moonlit ocean, while the ship that made it has no lights, no flag, and no outline, only gravity. In most galaxies, supermassive black holes are expected to live near the center, buried in the dense heart of stars and gas, anchoring the motion around them in ways that are difficult to see directly but clear through their effects. Our own Milky Way has Sagittarius A star at its core, a compact object with about 4 million solar masses, revealed not because anyone sees a black sphere hanging in space, but because stars near the galactic center whip around an invisible mass at incredible speeds. That kind of evidence taught astronomers one of the most important lessons of modern astrophysics. Black holes are not myths, but they are rarely seen in the simple way our eyes want to see things. They reveal themselves through motion, heat, radiation, distortion, and absence. This suspected runaway black hole follows that same rule, only in a far more dramatic setting. Instead of being recognized by stars orbiting tightly around it, it may be recognized by the path it cuts through space. The idea is unsettling, because a supermassive black hole should not casually wander outside its galaxy. It is not a loose asteroid or a rogue planet drifting after a mild gravitational nudge. To move something with millions of solar masses out of a galactic center, the event behind it must be enormous. Something had to give it speed. Something had to break the quiet expectation that the heaviest object in a galaxy's core stays there. And that is where the story moves from observation into cosmic crime scene investigation. The bright end of the trail may mark the current position of the fugitive, or at least the region most affected by it. Researchers have described a compact, bright knot near the tip, and that detail matters because a moving black hole would not necessarily glow by itself, but the material around it might. If gas is compressed in front of a massive object traveling at high velocity, it can be shocked, heated, ionized, and forced into conditions that make it shine. Some of that gas might also be drawn toward the black hole, forming a small accretion structure where friction and gravity heat matter before it disappears. That would not mean the black hole is blazing like a quasar, because this object, if real, may be moving too quickly and too cleanly through thin gas to feed in the classic way. But even a modest amount of disturbed material could create a signpost, a faint flare of activity that tells astronomers where to look. This is why the head of the trail is so important. It is not merely the front of a line. It is the place where the invisible suspect may be interacting with its surroundings right now, or at least where the light from that interaction began its long journey toward us. The deeper logic is elegant. If a black hole is moving through gas faster than the local speed at which pressure waves can travel, it may create a bow shock, similar in broad concept to the wave at the front of a boat or the compressed air ahead of a supersonic aircraft. In space, of course, there is no neat earthly ocean, no atmosphere like ours, and no sharp white sonic boom cloud. There is only thin gas, gravity, radiation, and time. But the principle of compression still matters. A fast-moving mass can disturb what it passes through. If the suspected black hole is plowing across intergalactic space, the gas ahead of it may be squeezed and heated, while the region behind it may cool and fragment into stars. That would make the black hole both hidden and traceable, a dark bullet whose path is written in light. Yet, this is exactly where the careful language matters most. Scientists do not have the luxury of saying, "There it is," with absolute certainty simply because one explanation is exciting. A bright knot could be shock-heated gas, but it could also be connected to another kind of energetic process. A linear feature could be a wake, but unusual jets and tidal structures must be considered. An object at the head of the streak could be the culprit, or it could be part of a more complex interaction that only appears simple from our viewing angle. The universe is three-dimensional, but telescope images arrive flattened onto a two-dimensional sky, and that can turn separate objects into apparent alignments or make curved structures look straight. This is why follow-up observations matter so much. Hubble gave the visual clue, but quasar-like activity, star formation, gas motion, and chemical signatures require different instruments and different wavelengths of light. A mystery like this is not solved by one beautiful image. It is squeezed slowly by evidence from every side until the weakest explanations fall away. Still, the runaway black hole interpretation remains powerful because it explains several strange features at once. It explains why the trail is so narrow. It explains why there may be young stars along the path. It explains why the leading region appears unusual. It explains why the structure seems tied to a galaxy that may have experienced a violent past. And perhaps most importantly, it explains the sense of direction, the feeling that this is not just material drifting, but the record of something moving. That movement is the emotional center of the chapter. A black hole is usually imagined as a destination, the final point toward which matter falls. Here, it becomes a traveler. It does not wait at the center. It is not calmly feeding in a galactic nucleus. It may be crossing the darkness between galaxies, stripped of its old throne, carrying its enormous gravity through a region where almost nothing can stop it. If it weighs around 20 million suns, then every second of its journey carries a kind of silent violence. Not the cinematic violence of explosions, but the deeper violence of gravitational history, mergers, close encounters, slingshot ejections, and the rearrangement of objects so massive that ordinary human ideas of force feel useless. The black hole itself would not know exile. It has no intention, no anger, no hunger in the human sense. But the image invites that language because the event is so rare from our point of view. A supermassive black hole outside its home galaxy feels like a king thrown from a castle, except the castle is a galaxy, and the king is a region of space-time from which light cannot return. That metaphor is not science by itself, but it helps carry the scale into the imagination, and scale is part of the truth here. 20 million suns, compressed into an unseen object, moving across intergalactic space, would be one of the most dramatic examples of gravity refusing to stay where we expect it. The most fascinating part is that such an object could remain unnoticed for ages if it did not disturb something bright. A runaway black hole moving through empty space would be nearly impossible to find. It could drift silently through the cosmic dark, not because it is small, but because it is dark and isolated. Only when it passes through gas, triggers shocks, or leaves star formation behind does it become visible indirectly. That raises a larger question without needing to exaggerate. If this candidate is real, how many others might exist without trails bright enough for us to see? Galactic mergers are common across cosmic history. Supermassive black holes likely interacted many times as galaxies grew from smaller systems into larger ones. Some may have merged, some may have formed binaries, and a few may have been kicked away by gravitational encounters or recoil from black hole mergers. Most would not leave a perfect visible signature. They would be ghosts of galactic violence, wandering through the spaces between galaxies, detectable only under rare conditions. The suspected culprit at the head of this trail matters because it may be one of those rare conditions, captured at the right angle, at the right time, with the right telescope. It is not just a dark object. It is a test of how black holes move, how galaxies evolve, and how much of the universe's history is written not in the objects we see clearly, but in the disturbances they leave behind. And that is why the invisible suspect is more compelling than a visible monster would be. A glowing object could be admired and cataloged. A hidden object forces investigation. It makes every bright patch, every color, every alignment, and every measurement part of the story. The trail points forward, the galaxy points backward, and between them is a silent question traveling through deep time. Did Hubble catch the aftermath of a supermassive black hole being thrown from its galaxy, or is the universe showing us an even stranger kind of structure we have not yet learned how to name? For a black hole to run away, the universe has to do something far more extreme than simply nudge it out of place. A supermassive black hole is not a loose stone drifting near the edge of a galaxy. It is usually buried deep in the central region, surrounded by stars, gas, dark matter, and the long gravitational memory of everything that built the galaxy over billions of years. To remove something like that from its home, the galaxy itself must have gone through a violent rearrangement. the kind of event that does not look like a single explosion, but like a slow-motion catastrophe written across cosmic time. The most likely beginning is a galactic merger, because galaxies are not isolated islands forever. They move through space, gather into groups, pull on one another, and sometimes collide. From a human point of view, the word collision sounds like a crash, but when two galaxies meet, their stars usually do not slam into each other directly. The distances between individual stars are so huge that two galaxies can pass through each other like ghostly cities, each star mostly missing every other star. But gravity does not miss. Gravity reaches across the whole system. It stretches spiral arms, drags gas into long streams, stirs quiet disks into chaos, and pulls the dense centers of both galaxies toward a shared fate. If each galaxy has a supermassive black hole at its core, then the merger does not just blend stars. It brings two dark giants into the same gravitational arena. At first, those black holes may be separated by thousands of light years, each still wrapped in the remains of its old galactic center. But friction from stars and gas gradually steals energy from their motion, making them sink inward. Over time, they can become a binary pair, two massive black holes orbiting one another in the crowded heart of the newly merged galaxy. This alone is already dramatic enough, because the pair can disturb nearby stars, fling some outward, swallow gas, and reshape the center of the galaxy. But a runaway black hole likely needs an even messier story. The most compelling scenario begins when a third galaxy enters the picture, before the first pair has fully settled or merged. That third galaxy carries its own central black hole, and suddenly the system is no longer a slow dance between two partners. It becomes a three-body problem, one of the oldest and most famously unstable problems in physics. Two objects can orbit each other in a fairly predictable way, but three massive objects pulling on each other can become chaotic. Small differences in position or speed can grow into huge changes in outcome. One black hole may pass close to another, trade energy, swing around the pair, and leave with far more speed than it had before. This is not magic, and it is not a rocket launch. It is gravity acting like a slingshot. Spacecraft use the same basic principle when they fly near planets to gain speed, borrowing a tiny bit of momentum from a much larger body. Around black holes, the stakes become enormous. In the dense heart of a merged galaxy, three supermassive black holes can exchange energy so violently that one may be hurled outward, while the others recoil in the opposite direction or tighten into a closer pair. That image is almost impossible to picture at full scale. Three invisible gravitational engines, each millions or billions of times heavier than the sun, whipping around one another in a region packed with stars, until one is ejected like a dark cannonball from the center of the system. What makes this even more fascinating is that there are different ways a black hole can be kicked away, and scientists have to consider more than one possibility. The three black hole slingshot is one strong explanation for an object moving far from its galaxy, especially if there are signs of past mergers. But another kind of kick can happen when two black holes finally merge. As they spiral together, they release gravitational waves, ripples in spacetime that carry energy away. If those waves are emitted unevenly, the newly formed black hole can recoil in the opposite direction, like a gun kicking backward after firing. In some cases, models suggest that recoil could be strong enough to move a black hole away from the center of its galaxy, or even eject it entirely if the speed exceeds the galaxy's escape velocity. That idea is not speculation pulled from nowhere. Gravitational waves from merging black holes have been directly detected in other contexts, proving that black hole mergers do shake spacetime itself. The question in this particular case is which mechanism, if any, best matches the evidence. A gravitational wave recoil might send a merged black hole flying, while a three-body encounter might fling one member out before the others merge. Both are rooted in real physics, but they leave different fingerprints. A three-body slingshot may leave behind another black hole pair in the galaxy, possibly moving the other way. A merger recoil may leave a single remnant carrying the combined mass of the pair. The trail, the host galaxy, the bright regions, and any hidden activity near the center all become clues in deciding which story fits best. This is why the phrase runaway black hole is so powerful but must be handled carefully. It sounds like something with intention, as if the object chose to escape. But the real story is colder and more beautiful. It is not running because it wants freedom. It is moving because gravity rearranged the books of motion and gave it more energy than its old home could hold. Every galaxy has an escape velocity, a speed an object must exceed to leave and not fall back. For a supermassive black hole to cross that threshold, the interaction must be extraordinary, but not impossible in the long history of galaxy formation. The universe has had billions of years to create rare events. Rare does not mean unreal. It means most galaxies do not show them clearly, and most ejected black holes may be almost impossible to find. If a black hole leaves a galaxy and travels through near-empty space, it may carry no bright disk of gas, no blazing jet, no obvious signal. It could become a wandering gravitational shadow, only under special conditions, if it passes through gas dense enough to react, or if it drags a small cluster of stars with it, or if its motion shocks material into glowing, would it become visible to us. That is why the possibility of a runaway black hole is not just about one object, it is about a hidden population. If one has been caught because it happened to write a glowing signature behind it, there may be others moving unseen through the darkness between galaxies, silent evidence of ancient mergers we never witnessed. The larger meaning is that galaxies are not as calm as they appear in long exposure images. A beautiful spiral galaxy can look peaceful, its arms turning slowly like a cosmic wheel, but its past may include cannibalized neighbors, warped gas, swallowed star clusters, and central black holes that changed partners over time. Elliptical galaxies, which often look smooth and featureless, may be the worn-down results of older collisions. The centers of galaxies are not static monuments. They are busy gravitational courtrooms where the heaviest objects negotiate through force rather than words. When a third black hole intrudes into a binary system, there is no referee to keep the arrangement neat. The lightest of the three is often the most likely to be ejected, but lightest can still mean millions of suns. Sometimes the incoming black hole disrupts the existing pair. Sometimes the pair hardens, drawing closer together. Sometimes stars passing nearby are thrown outward too, carrying away energy and helping the black holes sink closer. Over enough time, these interactions can empty out the central region of stars, carve cores in galaxies, and set up the conditions for one object to be expelled. What feels like a sudden escape in a telescope image may actually be the final visible result of a long sequence of gravitational trades. And there is a subtle point here that makes the story feel even more real. A runaway black hole would not need to be perfectly aimed for us to see it as a long line. We are viewing from one angle across an immense distance. A path through space could look longer, shorter, straighter, or more connected depending on how it is tilted toward us. If the motion is mostly across our line of sight, the trail appears stretched on the sky. If it is angled toward or away from us, part of its true length could be hidden in depth. That uncertainty does not weaken the case. It reminds us how careful astronomers must be when reconstructing three-dimensional violence from two-dimensional light. The universe does not label its evidence. It gives us projections, colors, spectra, motions, and probabilities, and scientists have to rebuild the event like investigators studying tracks after a storm has already passed. The reason a black hole might run away, then, is not one simple push, but a chain of cosmic history. Galaxies fall together, their centers sink, black holes form pairs, another galaxy arrives, gravity turns orderly orbits into chaos, and one dark giant leaves with enough speed to cross spaces it was never expected to enter. It is a story that makes the universe feel less like a museum and more like a living archive of collisions. Even the most powerful objects can be displaced. Even the centers of galaxies can lose their anchors. And somewhere far beyond the familiar stars of the Milky Way, a black hole may be traveling not because it is chasing anything, but because long ago, in the crowded heart of a merging galaxy, gravity made a decision that light is only now beginning to reveal. Speed in space is deceptive because nothing out there gives the eye an easy reference point. On Earth, speed is noise, wind, vibration, a road blurring under headlights, a jet crossing the sky in a white flash. In deep space, even something moving faster than anything humanity has ever built can look frozen when viewed from billions of light years away. That is what makes this suspected runaway black hole so unnerving. The image is silent, The line is still. The galaxy does not appear to tremble, and yet the numbers suggest a violent escape in progress. Researchers have estimated that the object, if the runaway black hole interpretation is correct, may be traveling at roughly 4 million miles per hour. That number is so large, it almost slips out of human understanding, so it helps to slow it down in the mind. At that speed, something could cross the distance from Earth to the Moon in only a few minutes. It could circle Earth in less time than it takes many people to finish dinner. It is not moving like a planet in a calm orbit or like a star drifting patiently through a galaxy. It is moving like something that has been thrown with enough energy to leave its old gravitational home behind. But even that comparison is imperfect, because a black hole with millions of solar masses is not a bullet in any ordinary sense. It is a compact region of gravity so extreme that its motion is not just movement, it is a traveling disturbance in the structure around it. If this object is truly racing through intergalactic space, then its speed is part of the evidence, part of the mystery, and part of the reason the trail behind it could exist at all. A slow object might simply sink back toward the galaxy, or drift without leaving a dramatic mark. A faster one can push through thin gas, compress material, and leave behind a wake that remembers its path. The estimated travel time makes the story even deeper. Scientists have suggested the event may have been unfolding for around 39 million years, a span that sounds ancient until you compare it with the age of galaxies. To a galaxy, 39 million years is not a lifetime. It is a recent scar. To Earth, it is a world before humans, before cities, before language, before anyone could look at the night sky and imagine an invisible mass fleeing a galaxy far beyond the Milky Way. While mammals moved through forests and climates shifted across our planet, this distant object may have been crossing the dark between galaxies, laying down a path so immense that Hubble would one day catch the light from it as a single, thin streak. That is the strange patience of the universe. The most violent motions do not always arrive as explosions. Sometimes they arrive as geometry, as a line, as a measurement, as a speed calculated from distance and time. If an object has moved far enough from its galaxy to create a trail hundreds of thousands of light years long, then its motion is not casual. It is not a wobble around the center. It is not a temporary displacement. It is more like an escape trajectory, the kind of path that tells astronomers the object may have received enough energy to break free from the galaxy's central pole. Every galaxy has a gravitational grip, and escaping it is not easy. Stars can orbit for billions of years without leaving. Gas can be pulled back in. Even objects disturbed by collisions can remain bound if their speed is not high enough. To escape, a body must move faster than the local escape velocity, and for something born in the dense center of a galaxy, that requirement can be severe. This is why the suspected speed matters so much. 4 million miles per hour is not just an impressive statistic for a thumbnail. It is a clue that something extraordinary happened in the past. The object did not wander away gently. It was likely accelerated by one of the most powerful gravitational interactions nature allows. And because the suspected traveler is so massive, the energy involved is almost beyond ordinary imagination. Moving a mountain at high speed is impressive. Moving a star at high speed is cosmic. Moving a supermassive black hole at millions of miles per hour belongs to a different category altogether, where the event that caused it must involve the rearrangement of galactic centers, not local accidents. Yet the speed also creates a paradox. Black holes are famous for pulling things in, but here the black hole itself may be the thing that was flung outward. That reversal makes the story feel almost rebellious, as if the object most associated with capture became the object that could not be held. There is a deeper truth inside that image. Gravity does not only trap, it can also launch. When several massive bodies interact, they can trade energy in ways that send one object away faster than before. In everyday life, people think of gravity as downward, as falling, as weight. In the universe, gravity is also a slingshot, a sculptor, a thief of momentum, a hidden hand that can turn an orbit into an exile. If the black hole gains speed through a close gravitational encounter, then its motion is the leftover signature of a past system becoming unstable. The galaxy we see is not merely a location, it is the scene after the event. The black hole is not simply far away, it may be carrying the memory of the encounter in its velocity, and that velocity may be what keeps it from returning. A slower ejected object might arc outward and eventually fall back, like a stone thrown upward that cannot escape Earth. A fast enough object keeps going, crossing into the darkness between galaxies, where the density of matter drops and the old galaxy becomes less a home than a fading point behind it. This is why the phrase "fast enough to escape the galaxy" has such weight. It means the object may have passed a threshold. Below that threshold, its journey would be dramatic, but temporary. Above it, the journey becomes permanent, or at least permanent on timescales so vast that no civilization could wait around to see the end. There is also something haunting about the direction of the trail. A high-speed object moving through space turns time into distance. The farther back along the trail one looks, the older the disturbance may be. The younger, brighter regions closer to the leading end might mark more recent interaction, while material farther behind may preserve earlier stages of the escape. In that sense, the trail is not only a path across space, it is a timeline stretched across the sky. Instead of reading a graph, astronomers may be reading motion written in stars. The front tells one moment, the middle another, the far end another, each separated by huge distances and long spans of time. That is what makes the structure feel almost cinematic. A single object moving too fast to see directly, leaving behind scenes from different chapters of its journey. But the numbers must still be treated with care. The true speed depends on assumptions about distance, orientation, and the physical nature of the trail. If the path is tilted partly toward or away from us, the visible length on the sky may not represent the full journey. If the trail formed through a more complex process, the relationship between its length and the object's motion could be less straightforward. Science does not weaken itself by admitting that. It becomes stronger because every estimate is a way of saying, here is what the evidence suggests, and here is what still needs testing. The speed may be enormous, but the interpretation has to earn its certainty. More observations, especially in different wavelengths, can help reveal whether the bright regions match young stars, shocked gas, or some other energetic phenomenon. If the head of the trail shows signs of compressed gas, ionization, or a bow shock, that would support the idea of a massive object plowing through space. If the galaxy shows signs of past disturbance, or missing central activity, that would add another piece. The velocity is not standing alone. It is one thread in a larger web of clues. Still, even as a candidate, the idea is powerful, because it changes the way we picture black holes. They are not always fixed monsters at the centers of galaxies. Under rare conditions, they may become travelers. Some may roam silently with no visible trail at all. Others may move through gas and briefly reveal themselves through the stars they help ignite, or the shock waves they create. The suspected object in this story may be one of those rare visible cases, not because it is close or bright, but because it is fast enough to make the invisible visible. Its speed turns absence into evidence. Its motion turns darkness into a line of light. And if that interpretation is right, then somewhere at the leading edge of this enormous structure is a black hole moving so quickly that its old galaxy may never reclaim it. A dark mass carrying the violence of a forgotten encounter into the open spaces beyond, while the universe quietly records its escape in a trail long enough to dwarf the galaxy we call home. The strangest twist in this entire story is that the suspected black hole may not be remembered by what it swallowed, but by what it helped create. That almost feels wrong at first, because black holes have become one of the most powerful symbols of cosmic destruction. Invisible mouths, collapsed gravity, regions where matter vanishes from view and light loses the fight to escape. Popular imagination usually turns them into endings. A star wanders too close, gas spirals inward, radiation flares, and whatever crosses the point of no return is gone from the observable universe. But the possible runaway black hole seen through Hubble's clues suggests a more complicated picture, one that is not softer, but deeper. In this case, the black hole may be moving so quickly through thin gas that it does not simply sit and feed like a monster at a banquet. Instead, it may be acting more like a dark plow, cutting through a faint cosmic medium and forcing that material into new conditions. The key is pressure. Space between galaxies is often described as empty, but empty does not mean absolute nothing. There can be extremely thin gas spread across enormous distances, so faint that it would be invisible unless something disturbs it. A supermassive black hole moving through that gas at tremendous speed would not need to touch it in the ordinary sense. Its gravity, motion, and the pressure of its passage could compress the surrounding material, creating shocks and dense pockets where gas begins to cool. And in the universe, cooling gas is not a small detail. It is the first step towards star birth. Gas that remains hot and spread out resists collapse. Its particles move too quickly, pressure pushes outward, and gravity cannot easily gather it into a star. But when gas is squeezed and loses energy, gravity gains the advantage. The material can clump, then fragment, then collapse into knots dense enough for new stars to ignite.
That is why the trail behind this object is so fascinating. If the blue light along it truly comes from young stars, then the black hole did not leave only a wound. It may have left a nursery. Not because it intended to create anything, and not because black holes are gentle, but because cosmic violence can rearrange matter into forms that become bright. This is one of the hardest truths about the universe to hold in the mind. Creation and destruction are often not opposites. They are different stages of the same physical process. A shockwave from a dying star can seed space with heavy elements. A galactic collision can tear old structures apart while igniting new star formation. A black hole can strip, heat, and consume matter in one setting, but in another, its motion can compress gas into the conditions needed for stars to form. The suspected runaway black hole belongs to that stranger category, where the same gravitational power we associate with erasure may have triggered a chain of blue, short-lived stars behind it. Young massive stars are important because they do not last long by cosmic standards. They burn hot, shine blue, and live fast. So when astronomers find a long blue feature, they are not simply admiring color, they are reading age. Blue stars suggest recent formation, which means the trail may be actively tied to the event, rather than being an ancient string of stars pulled out of a galaxy long ago. That detail matters because a trail of old stars would tell one kind of story, a story about tidal stripping and gravitational debris. A trail of newly formed stars tells another, sharper story. Something passed through and changed the gas itself. The black hole, if it is there, may be moving too fast to capture much material. This sounds counterintuitive, but speed changes the interaction. A black hole sitting in a dense galactic center can feed because gas has time to settle, spiral, heat up, and form a bright accretion disk. A black hole racing through thin space may not have that luxury. It could disturb more than it consumes. Material in front of it might be squeezed and shocked. Material behind it might settle into a wake. Instead of a glowing disk wrapped around the black hole, the most visible signature could be the aftermath spread across the path behind it. That is why comparing the feature to the wake behind a ship is useful, even though the real physics is far more extreme. A boat does not carry the ocean with it. It moves through the water and leaves a pattern where its motion changed the surface. In this case, the suspected black hole would be moving through gas, and the pattern would not be waves on water, but compressed regions, shocked material, and possible star formations stretched across intergalactic space. There may also be a leading shock, a region ahead of the object where gas is pushed and heated before flowing around or behind it. If such a feature is confirmed, it would strengthen the idea that something massive is moving through the medium rather than a structure simply sitting in place. But the evidence has to be handled carefully because nature often offers more than one way to make a strange shape. A jet from an active black hole can also create long structures. Interactions between galaxies can pull out streams of stars and gas. A chance alignment of distant objects can make separate features appear connected. A cloud of gas, shocked by a different event, might mimic part of the expected signal. The reason the star formation interpretation is so compelling is not that it is the only imaginable explanation, but that it ties several clues together. The narrow path, the blue light, the possible bright knot, the connection to a disturbed galaxy, and the scale of the structure. In science, a good explanation does not simply sound exciting. It earns attention by explaining more than one odd fact at the same time. Still, the word possible should remain close to the story. If the trail truly marks newborn stars behind a runaway black hole, then astronomers may be seeing something rare enough that there are few close examples for comparison. That means every detail becomes important. The color of the light matters, the spectrum matters, the distribution of brightness matters. Whether gas appears ionized matters. Whether the host galaxy shows signs of a recent merger matters. Whether there is X-ray emission or infrared evidence near the leading edge matters. Each wavelength acts like a different kind of witness, and no single witness tells the whole truth. Hubble gave the scene its shape, but the physics inside that shape must be reconstructed from multiple clues. That process is not as fast as a dramatic headline, but it is more satisfying because it lets the mystery breathe. The deeper idea is that black holes do not exist outside the rest of the universe. They are part of its ecology. They regulate galaxies by heating gas, launching jets, disturbing star formation, and sometimes shutting it down. In other cases, they may help trigger it. A black hole feeding violently at the center of a galaxy can blast energy outward and prevent gas from cooling, starving the galaxy of new stars. But a moving black hole passing through the right environment could do the opposite locally, squeezing gas into bright new knots. So the question is not simply whether black holes destroy or create. The better question is, under what conditions do they do each one? That is where this runaway candidate becomes valuable. It may show a black hole outside the familiar central role, not as a stationary engine, but as a moving force, interacting with gas in a way astronomers rarely get to see. And there is something quietly haunting about the stars it may have created, because those stars would owe their birth to an exile. They would shine behind an object they can never catch, formed from gas disturbed by something dark and already moving on. The black hole would continue ahead, almost invisible. The stars would remain behind, burning brightly for a short cosmic moment before aging, exploding, or fading into the broader history of the universe. If that picture is right, the trail becomes more than evidence of speed. It becomes a record of transformation. A dark object passes through thin gas, pressure rises, matter collapses, and light appears where there was once only faint material spread across the void. That does not make the black hole a creator in any mystical sense. It makes the universe more interesting than our simple categories. The same object that can erase light from view can also, under the right circumstances, leave conditions where new light begins. And that is why this chapter of the story is so gripping. The suspected runaway black hole is not terrifying because it is racing toward us, and it is not fascinating only because it is massive. It is fascinating because it may have turned motion into a trail of stars, proving that even the darkest things in the cosmos can sometimes be found by the brightness they leave behind. Hubble gave astronomers the shape of the mystery, but a shape alone is never enough. A telescope image can be beautiful, unsettling, even persuasive, yet the universe has a long history of fooling the eye, and scientists know better than to trust a strange line just because it looks meaningful. That is where the W.M. Keck Observatory in Hawaii becomes crucial, because Keck did not simply take another picture and admire the same streak from a different angle. It helped break the light apart. That may sound less dramatic than a new image, but in astronomy, splitting light into its colors can be more revealing than seeing the object itself. A picture shows where something is. A spectrum begins to show what it is, how it is behaving, and whether it belongs to the same distant scene or merely appears to by coincidence. The Keck telescopes sit high on Mauna Kea, above much of Earth's thick, turbulent atmosphere, in one of the best observing sites on the planet. From there, astronomers can collect faint light from objects so distant that every photon feels like a messenger arriving late from a vanished era. When Keck turned its power toward the strange Hubble feature, the question was direct. Is this line a real astrophysical structure, or is it some kind of visual accident dressed up as a discovery? The answer did not come as a loud announcement from space. It came through the fingerprints hidden in the light. Spectroscopy works because atoms and molecules do not shine randomly. Hydrogen, oxygen, and other elements leave specific marks in light, like coded signatures. And when those signatures are shifted by cosmic expansion or motion, astronomers can estimate distance and physical conditions. If the streak had been an instrumental flaw, there would be no meaningful spectrum to read. If it were a nearby object crossing the frame, its light would not match the deeper cosmic environment. If it were an unrelated background galaxy aligned by chance, its distance and properties might betray that separation. Keck's role was to test whether the line had the kind of physical reality that a camera artifact could never have.
And that is where the discovery gained weight. The streak was not just sitting on the image like a scratch. It showed signs consistent with real light from real matter, tied to an event in deep space rather than a defect inside the telescope. This is the moment when the story changes from Hubble noticed something odd to the odd thing survived a serious test. That distinction matters because extraordinary cosmic claims do not become stronger by sounding dramatic. They become stronger when the ordinary explanations begin to fail. Keck helped rule out the easy dismissal. The feature was not simply a cosmic ray hit on Hubble's detector. It was not just a processing error. It had structure, light, and behavior that demanded interpretation. What Keck could provide was not necessarily a final verdict that a runaway black hole had been found, but something almost as important: confirmation that the trail was worth taking seriously. The light along the feature suggested a physical system involving gas and young stars, the kind of evidence that makes the runaway interpretation possible in the first place. The blue appearance seen in the Hubble data already hinted at young, hot stars, but color alone can mislead. Spectroscopy gives that suspicion a firmer foundation by letting scientists examine the light with more precision. In the same way a doctor does not diagnose a hidden illness from a shadow on a scan alone, astronomers do not build a cosmic explanation from a line in an image alone. They test the light. They ask what elements are glowing. They ask whether the gas is excited, whether stars are young, whether the object shares a redshift with the suspected host galaxy, whether the trail appears physically connected or just visually aligned. Keck made the mystery less like a photograph and more like evidence. And once evidence begins to accumulate, the scene becomes more cinematic, not less, because now the viewer is no longer staring at a strange mark. They are watching an investigation unfold across wavelengths, instruments, and logic. Imagine that faint trail not as a white line on blackness, but as a ribbon of information stretched across space. Some parts may be dominated by young stars. Some may carry signs of ionized gas. Some may reveal shock, motion, or heating. Each section of light can tell a slightly different part of the story, and Keck's task was to begin translating that light into physics. If stars are being formed along the wake, their light should carry the signs of youth: hot, massive, blue stars that have not had time to age into cooler colors. If gas is being shocked, its emission lines may reveal that it is not calmly drifting, but has been energized by something forceful. If the whole structure belongs to the same distant system, its light should be shifted in a way that matches the cosmic distance of the associated galaxy. These are not decorative details. They are the difference between a mystery that can be told and a mystery that can be tested. There is a quiet discipline in this process that makes the story more believable. Nobody needed to pretend Keck had photographed a black hole tearing through space with a visible outline. It did not. Nobody needed to claim every doubt vanished overnight. It did not. What Keck helped show was that the trail itself was not imaginary, and that its light carried the kind of information expected from a real, distant, energized structure. In science, that is a powerful step. It means the question can move forward. Instead of asking whether the streak exists, researchers can ask what created it. That shift is enormous. A false mark ends the story. A real trail opens the door to physics. And the physics here is rare enough to be thrilling. If the trail contains newly formed stars, then something compressed the gas. If the leading region shows unusual excitation, then something may be disturbing the material at high speed. If the structure points back toward a galaxy with signs of past interaction, then the suspected escape begins to look less like a wild idea and more like a plausible reconstruction. Keck did not remove all uncertainty, but it gave the mystery a skeleton strong enough to carry the next questions. This is also why the observatory itself feels like part of the story. Hubble floats above the atmosphere, free from the blur of air, able to resolve delicate shapes in deep space. Keck, anchored on a volcanic summit, gathers light with huge mirrors and dissects it with instruments that can read details the eye will never see. One telescope catches the ghostly form. Another interrogates the light. Together, they turn a visual oddity into a scientific case. That partnership is how modern astronomy works now. The greatest discoveries rarely come from one heroic image alone. They come from layers: optical images, spectra, infrared observations, X-rays, radio data, computer models, and repeated checks against every boring explanation that might be true. The boring explanations matter because they are the gatekeepers. If a claim cannot survive them, it should not survive. But when a claim does survive, when the odd line remains real after the skeptical questions, it becomes far more compelling than a headline ever could. The Keck observations gave astronomers permission to treat the streak as a physical clue, and that changed the emotional temperature of the discovery. Now the line was no longer just strange, it was active. It was telling a story in light. It had the potential to reveal motion, violence, and star formation outside the normal boundaries of a galaxy. And still, the careful uncertainty stayed alive. Could this be a rare kind of jet? Could it be a tidal feature seen from an unusual angle? Could a complex interaction between galaxies mimic the shape of a runaway wake? These questions remain part of the drama because they keep the investigation honest. A weaker script would declare the answer too early. A stronger story lets the evidence tighten slowly. Keck made the illusion explanation much harder, but it did not turn the universe into something simple. Instead, it deepened the puzzle. The streak was real, but reality can have more than one cause. The trail carried signs of stars and gas, but the engine behind those signs still had to be identified. That is what makes this chapter so important. It is the point where the mystery survives contact with measurement. The strange line becomes more than a visual hook. It becomes an object that can be studied, questioned, challenged, and compared with models of how black holes, galaxies, and gas behave under extreme conditions. And in that survival, the suspected runaway black hole becomes harder to ignore. Somewhere in that thin, glowing structure, Keck helped reveal that the universe had left more than a mark. It had left evidence. Not final proof, not a closed case, but evidence strong enough to pull astronomers deeper into the chase, toward the bright knot at the front of the trail, where the invisible culprit may have disturbed the gas most violently, and where the next clue waits like a spark at the edge of darkness. At the leading edge of the trail, the story tightens around a small, bright knot, a concentrated glow that looks almost modest compared with the enormous structure behind it, yet may hold the most important clue in the entire scene. In deep space images, brightness is never just brightness. It can mean young stars, heated gas, scattered light, active feeding, shock waves, or a misleading overlap of objects at different distances. Here, the knot matters, because it sits where the suspected runaway object would be expected to disturb its surroundings most violently, like the glowing pressure point at the front of a long, invisible collision. If a supermassive black hole is truly plowing through thin intergalactic gas, the region ahead of it would not remain calm. Gas in its path could be compressed, stripped, heated, and electrically transformed. Astronomers call this ionization, but the idea is simple enough to picture. Energy has hit the gas so hard that electrons are knocked away from atoms, turning ordinary neutral material into a charged, glowing plasma. That glow becomes a signal. It tells researchers that something energetic happened there, something stronger than quiet starlight drifting through space. The bright knot may be gas shocked by the object's motion, heated as it is pushed aside at extreme speed, or it may be connected to material falling toward the black hole itself. Both possibilities are fascinating, and neither should be treated casually. Shock-heated gas would support the image of a dark mass moving like a high-speed projectile, forcing the surrounding medium to react. Accreting gas would suggest that even while racing through sparse space, the black hole may still be capturing enough material to create radiation near its path. The difference is subtle, but important, because one explanation emphasizes the black hole's movement through the environment, while the other emphasizes the environment feeding the black hole. In reality, both processes could even be happening together, with gas being compressed ahead of the motion, while some material is drawn inward and heated near the object. That is the kind of complexity that makes the knot so valuable. It is not just a bright dot, it is a laboratory for extreme physics, hidden inside a distant line of light. If the object is moving faster than pressure waves can travel through the gas around it, then a bow shock may form ahead of it, something like the curved wave in front of a boat or the compressed air ahead of a supersonic aircraft. The comparison is useful, but it has to be held lightly
because this is not water or air. It is a thin cosmic medium spread across distances so vast that our everyday sense of matter fails. Still, the basic idea remains powerful. When something moves too quickly through a medium, the medium cannot move out of the way smoothly. It piles up, heats, and glows. The knot at the front may be that pileup made visible, a bright scar where motion becomes energy. If so, then the object causing it does not need to shine directly. The surrounding gas becomes the witness. It is almost like tracking a predator in darkness by the snapped branches and disturbed ground it leaves behind. Except here, the ground is intergalactic gas, and the predator may be a black hole weighing millions of suns. But the knot also raises a harder question. If this is the head of the wake, why does it glow the way it does? The answer depends on what kind of light is coming from it. Hot young stars would produce one signature. Shocked gas would produce another. Gas near an active black hole might show still another. That is why astronomers care so much about emission lines, those narrow fingerprints in the spectrum that reveal which elements are present and how energized they are. Hydrogen glowing in a certain way can point towards star formation or ionized gas. Oxygen lines can reveal higher energy conditions. The width and shift of these lines can hint at motion, turbulence, or violent heating. To a casual viewer, the knot is a point of light. To an astronomer, it is a coded message. The challenge is that the message is faint, distant, and mixed with the broader light of the trail and the galaxy behind it. Reading it requires patience and skepticism. If the knot shows signs of strong ionization, that does not automatically prove a runaway black hole is there. Other engines can ionize gas. Massive young stars can blast nearby material with ultraviolet radiation. A jet from an active galactic nucleus can shock gas along a narrow path. A collision between gas clouds can create bright compressed regions. Even a rare alignment can make unrelated sources appear connected from Earth's point of view. These alternatives are not boring obstacles. They are part of the drama. The strongest scientific explanation must survive them. A runaway black hole is exciting because it can tie the knot, the trail, the possible star formation, and the distant galaxy into one coherent sequence. But coherence is not the same as certainty. The knot must behave like the front of a moving system, not merely look like one. That is why its position is so intriguing. It appears at the end where the motion would point, not randomly in the middle or off to the side. If the trail is awake, then the knot may be the place where the invisible traveler is currently driving into new gas. If the trail is something else, then the knot may be the anchor of a different mechanism entirely, perhaps a compact star-forming region, a small galaxy, or an energetic structure associated with a jet. The truth depends on how all the clues line up: shape, color, spectrum, distance, orientation, and the physical state of the gas. The most cinematic version of the scene is easy to imagine. A dark mass races through space. A shock forms ahead of it. Gas flares at the front, stars ignite behind it, and a glowing path records the journey. But real astronomy is not built by imagination alone. It asks whether the gas temperature makes sense, whether the star ages match the travel time, whether the brightness is consistent with the amount of available material, and whether simulations can reproduce such a narrow, extended feature. That last point is especially important because the universe does not always behave the way a clean drawing suggests. Gas can be clumpy. Magnetic fields can shape flows. Radiation can cool or heat material unevenly. A black hole moving through such an environment might leave a trail that is patchy rather than smooth, bright in some places and faint in others. The knot could represent a stronger collision with a denser region of gas, a place where the invisible object hit material thick enough to announce itself more loudly. If that is true, then the trail is not merely a line. It is a changing record of the medium the object crossed. Some regions would respond weakly, others strongly, and the bright knot would be the most dramatic response. There is something almost unsettling about that idea, because it means the black hole would be invisible not because it is absent, but because space is usually too empty to expose it. Only when it meets enough material does the darkness gain an outline. The knot may be that outline, brief and indirect, a flare of evidence around a thing that cannot be seen. It also changes the emotional rhythm of the discovery.
Until this point, the trail can be understood as aftermath, the long record behind the object. The knot feels more immediate. It is the front edge, the place where the story is still happening in the frame of the ancient light we receive. It gives the image direction. Without the knot, the line might feel like debris. With it, the structure feels like motion.
The eye wants to follow the trail toward the bright point, and the mind wants to ask what is hidden inside or just beyond it. That is why this small glowing region is so powerful for the investigation. It may be where the invisible becomes almost visible. Not directly, not as a black sphere with a boundary we can draw, but through the reaction of everything unlucky or fortunate enough to lie in its path. If future observations show X-rays from hot gas, infrared signatures of young stars, or spectral patterns consistent with shocks, the runaway interpretation becomes harder to dismiss. If instead, the knot resembles a different astrophysical source, the story may have to change. Either outcome has value, because the knot is the pressure test for the whole idea. It asks whether the proposed black hole is truly there, moving at the head of the structure, or whether the universe has arranged another rare phenomenon into a shape that fooled the first glance. That uncertainty is not a weakness in the story. It is the reason the story feels alive. The bright knot is a question mark made of ionized gas, suspended at the edge of a trail long enough to dwarf galaxies, and it may be showing us the exact place where a dark traveler is forcing the universe to glow. The suspected parent galaxy sits at the quieter end of the story, and that quietness is exactly what makes it dangerous to ignore. At first glance, it may look like just another distant galaxy, one more faint system among countless others scattered through deep space. But if the runaway black hole interpretation is correct, this galaxy is not just scenery. It is the scene of an ancient gravitational crime. It may be the place where the black hole once lived, the place where several massive objects came together, and the place where a chain of events began that ended with one of the universe's darkest giants being thrown into intergalactic space. The problem is that galaxies do not preserve their histories in clean, readable pages. They are more like old battlefields after wind and time have softened the tracks. A collision that happened tens of millions of years ago, or longer, may no longer look like a fresh wreck. The spiral arms may have been disturbed and then partly settled. The gas may have been pulled inward, heated, consumed, or pushed away. Star formation may have flared and faded. The central region may have rearranged itself into something smoother than the violence that made it. So when astronomers look back toward the galaxy connected with the trail, they are not looking for a single smoking crater. They are looking for subtle signs: disturbed structure, unusual alignment, missing activity, stretched light, possible companions, and the kind of shape that suggests the galaxy was not always alone. This is where the story becomes deeper than a runaway object. A black hole does not simply escape from nowhere. If one truly left this galaxy, then the galaxy itself must carry some memory of the event. In the standard picture, large galaxies grow by merging with smaller ones, and those mergers carry stars, gas, dark matter, and central black holes into new arrangements. From far away, the process can look deceptively graceful, but inside it is a slow gravitational storm. Stars are pulled into new orbits. Gas clouds collide and compress. The central black holes, once separated by the cores of their original galaxies, begin sinking toward the merged center. If the system involved more than two galaxies, or if one merger followed another before the first had finished settling, the core could become a crowded arena of black holes. The suspected host galaxy may therefore be more than a birthplace. It may be the survivor of a chaotic sequence, a system that once swallowed a companion, or was swallowed into a larger structure, leaving behind a central region where gravity became unstable enough to eject one member. That possibility matters because it changes how we read the image. The trail points outward, but the explanation points backward. Every bright patch along the path asks what happened at the origin. Was there a pair of supermassive black holes already locked in orbit? Did another galaxy fall in, bringing a third black hole into the center? Did the interaction fling one black hole outward, while the remaining pair recoiled in the other direction? Or did two black holes merge and receive a gravitational wave kick strong enough to push the remnant from the nucleus? These are not small differences. They are different versions of the galaxy's past. A three-body slingshot suggests a messy, multi-galaxy encounter.
a kind of cosmic billiards, where one black hole gains speed at the expense of the others. A gravitational wave recoil suggests the final union of two black holes, with space-time itself carrying momentum away unevenly and launching the merged remnant in response. Both ideas are grounded in real physics, but each would leave different traces in the host. A remaining binary black hole might still disturb the galactic center. A recoiling merged black hole might leave the center unusually quiet or displaced.
Gas near the nucleus might reveal whether an active black hole still sits there, or whether the original central engine has been removed. The absence of a bright active nucleus, if confirmed, would be intriguing, though not conclusive, because many galaxies simply have quiet central black holes that are not feeding strongly at the moment. That is the caution running through this chapter. A clue is not a verdict. A galaxy can look calm and still hide a central black hole. A merger remnant can look disturbed for reasons unrelated to an ejection. A faint feature near the galaxy might be connected to the event, or it might be a separate structure projected along the same line of sight. The universe is generous with coincidences when distances are this vast. But the pattern is what keeps the case alive. A long, narrow trail appears to lead back toward a distant galaxy. The galaxy may show signs consistent with an unsettled past. There may be features on the opposite side that raise the possibility of recoil, or a remaining black hole pair. And the suspected moving object seems to occupy the far end of a structure that behaves less like random debris and more like a path. The parent galaxy is therefore not just the background, it is the anchor that gives the trail a history. Without it, the line could be an isolated oddity. With it, the line becomes part of a larger event, one that begins in the dense center of a galaxy and continues into the space beyond. There is also a haunting time delay built into this view. The light from such a distant system has traveled for billions of years before reaching us, which means we are not seeing the galaxy as it is today, if today even has a simple meaning across cosmic distances. We are seeing an old chapter of its life, a chapter written when the universe itself was younger. The collision, the ejection, the formation of the trail, and the light now entering our telescopes all belong to a cosmic past that has only just arrived in human awareness. That turns the host galaxy into a time capsule. Its faint shape may preserve evidence of a merger that happened long before Earth's modern night sky had anyone to interpret it. And still, the physics is familiar enough to connect with what we know closer to home. The Milky Way itself is expected to merge with the Andromeda galaxy in the far future. When that happens, the central black holes of both galaxies will eventually interact as the systems combine. Most stars will not collide directly, but the galaxies as wholes will transform. Gas will shift. Orbits will change. The central black holes may spiral inward over enormous timescales. That future helps make the distant host feel less like an exotic exception and more like a preview of processes that shape galaxies everywhere. The suspected parent galaxy may simply have lived through a version of that fate earlier, with an extra complication violent enough to launch its central darkness into the void. To understand the signs of the collision, astronomers look for asymmetry, because undisturbed galaxies often have a kind of order, a disk, a bulge, spiral arms, or a smooth, elliptical glow. Mergers leave disorder. They can create tidal tails, shells of stars, warped disks, off-center brightness, and strange knots of star formation. Over time, these signs fade, but they do not vanish immediately. A galaxy that has recently merged may look slightly torn, stretched, or unbalanced. Its light may show younger stars in places where gas was compressed. Its outskirts may contain faint streams from a swallowed companion. Its nucleus may be shifted or depleted. None of these clues alone proves a runaway black hole, but together they help reconstruct whether the galaxy had the kind of violent past required. In this case, the most compelling idea is not that the galaxy exploded or suffered a simple impact. It is that its center became dynamically unstable. The real drama may have unfolded in a region too small and too distant for Hubble to resolve in satisfying detail, where several supermassive black holes exchanged energy until one was expelled. That hidden central violence would then explain the visible large-scale trail. The smallest unresolved region becomes the origin of the largest visible clue. There is a quiet irony in that. The host galaxy may appear faint and remote, but inside its past may be a gravitational event powerful enough to move a black hole across hundreds of thousands of light years. It reminds us that the centers of galaxies are not just decorative cores. They are engines of history. They decide how gas flows, how stars form, how galaxies grow, and sometimes, under rare conditions, whether a black hole remains home or becomes a wanderer. The suspected parent galaxy is therefore the emotional pivot of the story. Behind the glowing trail is not just speed, not just mass, not just shock-heated gas, but a broken relationship between a galaxy and the object that may once have anchored its heart. If that interpretation is right, the galaxy did not merely lose something heavy. It lost a central actor in its own evolution. And if the remaining center still contains another black hole, or even a pair of them, then the story is not over. The ejection would be one move in a larger gravitational game, with survivors still hidden in the galaxy's core. That is why astronomers keep looking back toward the origin. The trail shows where the possible fugitive went. The knot shows where it may be now. But the parent galaxy may reveal why it had to leave, and perhaps what was left behind when the darkness was thrown out. Picture the center of a merging galaxy, not as a peaceful core, but as a crowded room where the heaviest objects in the universe are being forced into the same space, with no simple way out. Two supermassive black holes may already be circling each other there, buried inside a storm of stars and gas left over from an earlier galactic collision, each one carrying the mass of millions or even billions of suns, each one bending the motions around it without making a sound. For a while, that pair can look almost stable in the language of gravity. They orbit, they lose energy to surrounding stars, they sink closer, and the galaxy slowly adjusts around them. But then a third galaxy falls in, and with it comes a third central black hole. That is where the calm breaks. The system is no longer a pair moving around a shared center. It becomes a three-body problem, one of the most famously unpredictable situations in physics, because three massive objects do not simply take turns politely. They tug, swing, steal energy, change direction, and amplify tiny differences into enormous outcomes. This is why scientists sometimes describe this scenario as cosmic billiards, but even that comparison feels too small. There is no table, no cue stick, no clean collision between solid balls. These objects may never touch at all. They play the game through gravity, across distances that would swallow entire star systems, and the prize is momentum. One black hole can pass close to the other two, dive through their gravitational field, and leave the encounter moving faster than before, while the remaining pair loses energy, changes orbit, or recoils in the opposite direction. It is the same broad principle that lets a spacecraft gain speed by passing near a planet. But here the players are not probes and planets. They are collapsed engines of gravity in the heart of a disturbed galaxy, and the speed gained can become large enough to turn an orbit into an escape. The strange thing is that the black hole most likely to be flung away is often not the biggest one, because in a gravitational exchange, the lighter member of a three-body system can be thrown out, while the heavier pair becomes more tightly bound. But lighter, in this setting, is almost a cruel word. A lighter supermassive black hole can still weigh millions of times more than the sun. Imagine something with that mass being accelerated not by an explosion, not by fuel, not by impact, but by the invisible bookkeeping of gravity. Energy has to go somewhere. Momentum has to be conserved. If one object leaves with a tremendous kick, the others respond. That response may be hidden in the host galaxy, perhaps as a pair of black holes still buried in the core, perhaps as a faint feature on the opposite side, perhaps as a central region that looks oddly disturbed or quiet. This is what makes the three black hole scenario so gripping. It does not just explain how one object could be thrown out. It predicts that the galaxy should remember the throw in more than one place. The possible runaway is one piece of the game, but the other pieces may still be on the board, invisible or nearly invisible, waiting for better observations to expose them. In a clean cartoon, the story is easy. Two black holes form a pair, a third one arrives, gravity slingshots one away, and a trail appears behind it. Real galaxies are messier than that. The black holes are surrounded by stars, gas clouds, dark matter,
and the shredded remains of smaller systems. As the black holes move, they scatter stars like tiny sparks in a dark room, sending some into wider orbits and using that exchange to tighten their own dance. Gas can drag on them, feed them, or get blasted away. The central region can be carved out over time as passing stars are ejected. If the black holes come close enough, gravitational waves may begin carrying energy from the system, slowly shrinking an orbit that was once too wide to merge. This means the cosmic billiards game is not a single instant. It can be a long, unstable chapter in the life of a galaxy, with quiet stretches, violent close passes, and sudden outcomes that only look sudden because we see the evidence long after the motion has played out. The suspected trail may be one of those outcomes frozen into light, a black hole that received enough speed to leave the nucleus, then crossed gas outside the galaxy, and turned its own escape into a luminous signature. The most interesting part is that the direction of the ejection may not be random. In a three-body interaction, the escaping object and the remaining pair should carry away momentum in different directions, like a recoil written across the galaxy. If astronomers see a long trail pointing away from a galaxy, they naturally ask whether there is something on the opposite side that hints at the other half of the exchange. It might be faint, it might be ambiguous, it might not be visible at all. But the question itself is powerful because it turns the image into a crime scene with missing suspects. One black hole may have fled. Two may have stayed behind or been kicked the other way. The galaxy's center may contain a binary black hole too close and too distant to resolve clearly. Or the remaining activity may be so weak that it leaves almost no obvious glow. That uncertainty is not a flaw in the story. It is part of why the story feels real. A headline wants a neat answer. A galaxy offers fragments. Scientists have to connect them without forcing the pieces to fit too early. The three black hole idea is attractive because galaxy mergers are not rare in cosmic history. Large galaxies grow by absorbing smaller ones, and many of those galaxies likely carried central black holes. Over billions of years, nature had many chances to create crowded black hole cores. Most of the time, the evidence would be difficult to see. A black hole ejected into emptier space might vanish from view. A remaining binary might sit quietly if there is not enough gas to feed it. A recoil might leave only subtle distortions in stellar motions that are too faint to measure at great distances. So when a possible trail appears, long and narrow and connected to a galaxy with signs of past disturbance, it becomes exciting not because it proves everything instantly, but because it may be one of the rare moments when the aftermath of that hidden game becomes visible. It suggests that black holes are not always just endpoints of collapse or silent anchors at galactic centers. They can become participants in a larger choreography, and under the right conditions, one of them can be thrown into the dark like a piece knocked from the board. But even the word knocked is misleading, because nothing solid strikes anything solid. Gravity does all the work. A close pass can bend a black hole's path, increase its speed, and redirect it completely. The same way a planet can redirect a spacecraft, except the numbers here are monstrous. If the fleeing object is moving at millions of miles per hour, the encounter that accelerated it must have transferred an enormous amount of energy. The remaining black holes would not be unchanged. Their orbit may tighten, making a future merger more likely. If they eventually merge, they could release gravitational waves. And if those waves are uneven, even the final remnant could receive another kick. In that sense, one violent event can set up the next. A galaxy merger can bring black holes together. A three-body encounter can eject one. The remaining pair can merge later. A gravitational wave recoil can shift the final remnant again. The life of a galactic center can become a chain of hidden launches, each one leaving clues only if the environment happens to glow. The suspected runaway trail may therefore be more than a strange object. It may be a visible frame from a longer film we almost never get to watch. And there is a deeper lesson in the physics, though it does not need to be stated like a lesson. The universe is not built around stillness. Even its central objects, the things we imagine as fixed anchors, can be displaced when larger histories collide. A black hole that once sat in the dense heart of a galaxy can be turned into a traveler because gravity is not only a force of capture, it is also a force of exchange. It can bind two objects together and throw a third away. It can build a galaxy and empty its center. It can hide a black hole for billions of years and then reveal its path through a line of stars. That is what makes the cosmic billiards scenario feel so cinematic, without needing fiction. The table is a galactic core. The balls are supermassive black holes. The cue is the arrival of another galaxy. The shot takes millions of years. And the mark left behind may be a glowing trail across intergalactic space, pointing back toward a moment when three dark giants met in the center of a galaxy, and gravity chose which one would be cast into the void. The next stage of the investigation belongs to telescopes that do not all see the universe in the same way, because a mystery like this cannot be solved by one eye, one wavelength, or one beautiful image. Hubble revealed the strange structure in visible light, the kind of light our own eyes would recognize if they were powerful enough to stare across billions of years. But visible light is only one language spoken by the cosmos. James Webb listens in infrared, where dust becomes less blinding, cooler stars and distant galaxies reveal themselves more clearly, and stretched ancient light can be studied with extraordinary sensitivity. Chandra listens in X-rays, where the most violent regions often betray themselves. Gas heated to millions of degrees, black holes feeding, shocks burning through thin plasma, and energetic particles pushed to extremes. If the suspected runaway black hole is real, these telescopes are not just extra cameras. They are different witnesses standing around the same scene, each noticing something the others might miss. Webb can ask whether the stars in the trail are truly young, whether the gas at the leading edge carries the fingerprints of shock, whether the bright knot behaves more like a region of star formation, or like material disturbed by a supersonic object. Chandra can ask a harsher question. Is there high-energy radiation where a black hole or shock-heated gas should be? A black hole moving through thin space may not glow brightly if it is not feeding much, but if gas is being violently heated near its path, X-rays could provide an important clue. The absence of strong X-rays would not automatically destroy the runaway idea, because a fast-moving black hole in a sparse environment might be faint, but it would narrow the possibilities. That is how science closes in on a truth, not by demanding one perfect sign, but by watching which explanations survive when the light is examined from every direction. The James Webb Space Telescope is especially powerful in this case because it can do more than make a sharper picture. It can take spectra across small regions, reading the chemical and physical fingerprints of the trail and its tip. If gas has been shocked by a supersonic object, certain emission lines should behave in ways that differ from ordinary star-forming clouds. If the bright knot is simply an HII region, a glowing cloud around young massive stars, its line ratios may look more like normal low metallicity star formation. If it is a bow shock ahead of a runaway black hole, the gas may show signs of fast radiative shocks, rapid cooling, and a sudden change in velocity. That last detail is important because motion is harder to fake than shape. A narrow line on an image can be interpreted in different ways, but if the gas at the tip changes velocity sharply across a small distance, and if that change matches the physics of a body plowing through a medium, the runaway case grows stronger. At the same time, this is exactly why the open questions remain so interesting. Some researchers have argued that deeper imaging and alternative readings may favor a different explanation. Perhaps the long line is not a wake behind a black hole at all, but an edge-on star-forming galaxy, a thin disk seen from the side, with the bright knot representing one of its star-forming regions. That alternative is not boring. It is dangerous to the headline, and that is what makes it useful. A serious mystery needs a serious rival explanation. If the structure is an edge-on galaxy, then the apparent trail might not be a trail. It might be a flattened galaxy whose shape, brightness, and star-forming regions happen to mimic the aftermath of a runaway black hole. If the structure is a true wake, then the edge-on galaxy interpretation should struggle to explain the direction, the kinematics, the shock-like signs, and the connection to the possible host. This is where Webb becomes almost like a courtroom instrument. It does not care which story sounds more dramatic. It measures light. It asks whether the gas is moving the way a wake should move, whether the ionization looks like shocks or star formation, whether the stars line up in age and position with a moving trigger, and whether the front of the structure carries the compressed signature of something racing through space. Chandra adds another layer, because X-ray astronomy is often where hidden violence becomes visible. Many black holes reveal themselves through hot accreting gas, but a runaway supermassive black hole may not behave like a classic active galactic nucleus. It may not have a large stable disk. It may not be feeding enough to blaze across the universe. That makes the search more delicate. A weak or absent X-ray signal could mean the black hole is starving, not absent. A compact X-ray source near the tip could be suggestive, but not automatically decisive, because energetic star-forming regions and other compact sources can also produce high-energy emission. The best evidence would come from agreement. Infrared spectra showing shock-like gas, optical data matching the trail structure, X-rays consistent with hot disturbed material, and models showing that a black hole of the inferred mass and speed could create the observed wake over the available time. Even then, astronomers would continue testing, because the universe has a way of punishing anyone who declares victory too early. What makes this chapter so compelling is that it sits at the edge between discovery and confirmation. The original image opened the door. Follow-up observations made the feature harder to dismiss. But Webb and Chandra moved the story into a more demanding phase, where the question is no longer simply, what does this look like? But, what does the gas know? Gas carries memory in its motion, temperature, ionization, and chemistry. If a dark object passed through it, the gas may still hold the bruise. If stars formed in its wake, their ages may preserve the timing. If the bright tip is a shock front, its spectrum may carry the pressure of the invisible object pushing ahead. If instead the structure belongs to a more ordinary but unusually aligned galaxy, the gas should tell that story too. This is why uncertainty does not weaken the episode. It raises the stakes. A fake certainty would be less interesting than the real tension between competing explanations. The runaway black hole idea is extraordinary because it would show a supermassive black hole outside the role we usually imagine for it, no longer hidden in the center of a galaxy, but crossing the space between galaxies and leaving behind a luminous record. The edge-on-galaxy idea is extraordinary in a quieter way, because it would show how easily cosmic perspective can fool even expert eyes, turning a distant, flattened system into what appears to be a trail of exile. Either answer teaches something valuable. One teaches us that galactic centers can throw out their darkest giants, and that those giants may trigger star formation as they flee. The other teaches us that the universe can arrange light into shapes that imitate violence so convincingly that only deeper spectroscopy can untangle the truth. For a viewer, that may be the most honest form of suspense. The mystery is not, scientists know everything and are hiding the answer. The mystery is that scientists have enough evidence to make a bold possibility worth pursuing, but not enough to pretend every door has closed. Webb may reveal a bow shock. It may reveal ordinary star-forming gas. Chandra may find high-energy support. It may find silence. Future observations may sharpen the picture until one explanation becomes clearly stronger, or they may expose an even more complicated system than either side expected. That is often how astronomy advances. It begins with a shape that should not be there, then becomes a debate, then becomes a set of measurements, and finally becomes either a discovery or a correction that improves the map. There is no shame in that process. It is the process. The cosmos does not give clean answers on demand. It sends ancient light through dust, distance, expansion, and time, then asks us to rebuild the event from fragments. And in this case, those fragments are unusually powerful. A long, luminous structure, a bright leading knot, a possible parent galaxy, signs of young stars or disturbed gas, and the question of whether a supermassive black hole is moving through the dark too quietly to see, except by the damage, pressure, and light it leaves behind. James Webb and Chandra do not remove the mystery by arriving late in the story. They deepen it, because they force every exciting idea to face the evidence hidden beneath the image. If the runaway black hole is confirmed, it will become one of the clearest signs that even the giants at galactic centers can be thrown into exile. If it is not, the investigation will still have revealed how thin the line can be between a cosmic trail and a cosmic illusion. And that is why the question remains open in the most gripping way. Somewhere inside the data, in the infrared glow and the possible X-ray silence, in the motion of gas and the age of stars, the universe has already written the answer. We are simply still learning how to read it. If a supermassive black hole can be pushed out of the place where we once expected it to remain almost permanently, then the universe is less settled than it appears in the clean images we admire from telescopes. A galaxy can look calm from a distance, soft and balanced, its light spread like a quiet island in the dark. But inside, its past there may be a record of collisions, swallowed companions, broken orbits, and invisible giants thrown into motion by forces too large to fit into ordinary imagination. That is the deeper meaning of this possible runaway black hole. It is not only about one object moving through space, it is about the uncomfortable realization that even the strongest anchors in the cosmos may not always stay anchored. For decades, the simple picture was easy to hold. Large galaxies have supermassive black holes near their centers, and those dark cores grow alongside the galaxies around them, feeding when gas falls inward, sleeping when fuel runs low, shaping their surroundings through gravity and radiation. That picture is still powerful. But nature rarely obeys the simplest version of our diagrams forever. If galaxies merge often, and if their central black holes are dragged into the same crowded region, then some of those encounters must become unstable. Some black holes may merge, some may form pairs, some may be kicked off center. A few, under the right conditions, may be thrown out altogether, turning from central engines into wandering remnants of old violence. The most unsettling part is not that one may have been found. It is that many others may exist with no bright trail at all. A black hole crossing a region empty of gas would be almost impossible to notice from Earth. It could drift through intergalactic darkness for millions or billions of years, carrying enormous mass but producing little light. A ghost not because it is weak, but because the universe around it is too thin to reveal it. We tend to think the unseen is rare because our eyes and instruments do not catch it. But astronomy has repeatedly taught the opposite lesson. Dark matter was inferred from motion before it was understood. Exoplanets were suspected before thousands were confirmed. Gravitational waves were predicted long before detectors finally heard them. Black holes themselves moved from mathematics to evidence through the behavior of stars, gas, and space-time. Again and again, the universe has forced humans to accept that the visible world is only the surface of a deeper machinery. A runaway black hole, if confirmed, would belong to that tradition. It would be a reminder that the cosmos does not need to glow to be active. Some of its most important events may be visible only through aftermath. A displaced center, a strange trail, a shock in gas, a missing nucleus, a pattern of stars that should not be there. And that idea changes how we look at deep space images. A faint line is no longer just a faint line. A distorted galaxy is no longer just a pretty shape. A quiet center may not be truly quiet. It may be quiet because something once there has been removed. The spaces between galaxies, often imagined as emptiness, may contain travelers we have barely begun to count. Rogue stars, stripped gas clouds, wandering planets, faint star clusters, and perhaps black holes that once ruled the hearts of galaxies before gravity exiled them. This does not mean the universe is chaotic in a meaningless way. It means order and violence are often part of the same history. Galaxies build themselves by merging. Stars form when gas collapses under pressure. Heavy elements are made in stellar deaths and explosive events. Black holes grow through the fall of matter and the union of other black holes. The calm beauty of the present is often the cooled surface of older turbulence. The possible Hubble trail captures that truth in a single visual idea: darkness moving through space, leaving brightness behind. Whether the final explanation is a runaway black hole or an unusually aligned star-forming system, the investigation still exposes something valuable about how fragile our first impressions can be. From far away, a structure can pretend to be simple. A line can be a wake, a galaxy, a jet, a tidal feature, or something not yet described well by existing categories. The only honest response is not to flatten the mystery too quickly. The better response is to let the evidence keep speaking. That is why this story feels larger than the object itself. It sits at the edge of what astronomers can currently prove, where imagination is allowed to follow the data but not outrun it. There is a special kind of suspense in that space. It is not the suspense of fiction, where the writer already knows the ending. It is the suspense of a real universe withholding the last piece. If the trail truly marks a black hole escaping its galaxy, then we may be seeing one of the clearest examples of a supermassive black hole in exile, a dark core transformed into a high-speed wanderer by the violent history of galactic mergers. If the trail turns out to be something else, the correction will not be a failure. It will sharpen the tools, refine the models, and teach scientists how easily cosmic structures can imitate one another across enormous distances. Either way, the universe wins by being more complicated than the first headline. For the viewer, the most valuable part of the story is not fear. This object is not a threat to Earth. It is far beyond our galaxy, locked in a scale of distance and time that makes ordinary danger irrelevant. The real power is perspective. Somewhere out there, galaxies have collided, centers have shifted, black holes have exchanged energy, and light from the aftermath has crossed the universe long enough to arrive in our instruments as a mystery. Human beings then take that faint evidence and try to reconstruct the event with mathematics, telescopes, skepticism, and patience. That is a remarkable thing. A species living around one ordinary star on one small planet can look at a distant streak of light and ask whether a supermassive black hole was thrown from its home billions of years ago. The question itself is humbling. It tells us that knowledge does not begin with ownership of the universe, but with attention to small irregularities. Hubble's greatest gift has never been only its beautiful images. It has been its ability to make us notice what does not fit: the strange, the faint, the off-center, the almost dismissed. These are often the places where new understanding begins. And as newer observatories continue to study the sky, more of these hidden stories may surface. Some may confirm what current theories predict. Others may force those theories to bend. The Vera Rubin Observatory will scan the changing sky with extraordinary reach. Webb will continue pulling detail out of infrared light. Chandra and future X-ray missions can trace high-energy events that ordinary light cannot reveal. Gravitational wave observatories may one day catch the deeper tremors of massive black hole mergers with far greater sensitivity. Each new instrument widens the net, and when the net widens, the universe tends to become stranger, not simpler. That is the final door this story opens. If a black hole can leave a galaxy, what else is moving unseen through the dark? How many galactic centers are not where they began? How many ancient mergers left behind quiet fugitives with no visible trails? How many lines in old telescope data are not errors, but clues, waiting for someone patient enough to question them? We may find that the cosmos is filled with lost engines, silent remnants, and displaced giants, all carrying the memory of collisions that ended long before their light reached us. Or we may find that this particular case teaches us a different lesson about how galaxies can masquerade as motion when seen from the right angle. Both possibilities are worthy of wonder. The important thing is that the question has been asked. A thin streak in deep space became a doorway into the lives of galaxies, the behavior of black holes, and the limits of what we think we know. And perhaps that is the most honest ending. Not a final answer carved in stone, but a wider darkness filled with better questions. Somewhere beyond the familiar stars, the universe may still be hiding objects massive enough to reshape galaxies and dark enough to pass unnoticed unless they disturb the light around them. Hubble may have caught one of those disturbances, a luminous trace of an invisible traveler. And whether it proves to be a runaway black hole or something even more unexpected, it leaves us with the same quiet realization. The universe is not empty, not still, and not finished revealing itself. It is moving in ways we are only beginning to see. And as this strange trail fades back into the darkness, we're left with one quiet question. How much of the universe is still moving unseen around us? Thank you for drifting through this mystery with Sleepy Space. Leave a comment telling me where you're watching from, and gently like and subscribe for more cosmic stories to fall asleep to.